Next up is MemComputing. John Beane is on to discuss some of their unique things. This is a little bit of a change of pace from some of the things we've been talking about thus far. I will say, just to open it up, that one of my favorite courses when I was in grad school was operational research. And a lot of what your video says is, how the heck do I make all this ops research with 100 different assumptions and moving parts? How do I find the path through here that is the most efficient or the least costly or whatever the case may be? And I think you've got an interesting capability that kind of begins to enable some of those decisions to be made for whatever consumer participates. So, John, over to you. Look forward to hearing to the discussion.
Hey, Scott and Adam, thanks so much. And yeah, MemComputing is an enabling technology, as you mentioned. So we're a new compute technology that was designed specifically to handle these operational research type problems. So things today that are combinatorial optimization problems, which is kind of a big set of words, but it really results in, kind of boils down to scheduling and routing type problems. And these problems actually scale exponentially as the inputs grow sequentially. And it's a problem with our current compute technology. I won't go into too much of the detail there, but we've actually built a solution that overcomes that. And we're able to solve these problems without scaling exponentially. In fact, we scale linearly in many cases. And so we're actually solving problems that are currently intractable today. So they would take years and even millennia in some cases to solve. So the key aspect to our technology is that we handle scale. So the larger the problem, actually, the better we do as far as performance goes. And it's also that we will solve these problems in orders of magnitude faster. So we were at the U.S. Air Force Space Catalyst in the fall of 2019, and that led to us receiving our first SBIR. And I should mention that we work in the commercial field, and we've been there for a number of years now. We're very big in, big being a relative term considering we're a small company, in transportation, logistics, and oil and gas. So those are our main markets commercially, but we've always seen a great opportunity on the DoD side and the space side. And we're really excited to have been brought into the Space Catalyst and then got our first SBIR. And as part of the first SBIR, we then searched for Air Force customers that might have problems that we could address. And we're fortunate enough actually to find 3. So I just want to bring those out because our technology is hard to understand, but it's easier to understand when you talk about the case studies of the use cases that we'll be applying against. So there's 2 in the satellite community. One is related to actually modeling the optimal performance on processing data. So you take your satellite data and your satellite, what you have is computational performance on the satellite and the amount of data, and then of course taking into account your communication throughput, then what you could do on the cloud, and then also the communication and throughput that might be available to the warfighter at the their mobile devices. And so we're actually, our first project is going to be just calculating the optimal compute that you should do at each stage, including taking into account the communication performance between those, so that you can make sure optimize the information and results to the warfighter. We're then also looking at another problem that's related to in the satellite space. You have to optimize your movement. So if in this case we're talking about a 2 satellites merging together, and you have to optimize the performance between those 2, and it's really because of just all the physics involved, there's a lot of computation associated with that, and that is computation that will go on the satellite. And so actually another thing that's really great about our technology is that we are in software today. Ultimately, we'll build a chip, but the beauty about being in software is that in theory, it can be uploaded to satellites that are in space today and increase the performance, increase their lifespan, and then ultimately, when we build a chip, which is our next generation, that can go into next generation satellites. And then the third project we're working on is on the strategic operations command side, where they're evaluating signal processing, and they use neural networks to do that. And neural networks themselves are pretty fast, but the issue you have with neural networks is the training. So MemComputing actually can also be used to accelerate and increase the accuracy of training on neural networks. So those are some of the use cases that we're going after. And the key aspect to it is that we can handle larger data sets and solve the problems, reduce the data faster and with larger data sets.
That's that's great information. I appreciate that. I've got a number of questions that are coming in, many of whom are very disappointed to see that all their expectations and the long quantum computing has been a waste of time, because you believe that you have capability today that can outperform anything that's likely to come anytime soon from quantum computing. Can you talk a little more about that?
Yeah, thanks for teeing that up. That's that's a key thing. So the issue has primarily been that with current technology, there is this lag, and we just haven't been able to squeeze more out of our current computers. And so our technology actually was invented at UC San Diego by two PhD physicists who actually went back to the drawing board, and they said, today, if I was going to design a computer knowing what I know today, we're talking at the chip level, so at the circuit level, how would I design that circuit to eliminate some of the bottlenecks that we have in current computers? And the key bottleneck that we have today is called the von Neumann bottleneck, and it's basically that your CPU and your memory are separate. And there's a lot of communication that has to go back and forth between the two. And that's really what causes a lot of these computational problems to grow exponentially in time. The bottom line of what we've designed is computational memory. So the memory and the compute is all together. And there's other physics things that we're taking advantage of. So we're actually a new compute architecture. But what's amazing about this architecture is that while it is, I said, ultimately we'll build a chip, how we're delivering it in software today is it's the emulation of the chip. And the chip is so efficient that we're delivering this performance that we talked about. And one other thing I should mention is that our technology is actually live today. So while a lot of the performance that we talk about, it sounds like it's too good to be true, but we have a SaaS model. It's free to use for evaluation, so people don't have to take our word for it. They're able to test it out themselves. But yeah, it's these physicists their background is also quantum computing and unconventional computing methods, basically sought to solve it using current capabilities, and were able to overcome these performance criteria. And we've actually done a number of benchmarks against quantum computing problems, and we're really kind of designed to solve the same problems that quantum computing is going after. I mean, quantum computing is going after combinatorial optimization problems. So it applies in other areas as well, including, drug design, genetic sequencing, portfolio optimization in fintech, and other areas. But like I said, transportation, logistics, oil and gas, and now the DoD side are our main markets.
Now, that's outstanding information, John. I appreciate that. And unfortunately, our time is up now. I want to leave enough time for the last presenter. But really, really advanced kind of capabilities you're talking about. I think it has a lot of applicability across the satellite developers, the ground, the comms, et cetera, as you mentioned. A lot of great work there. So look forward to hearing more from you in the future. But thanks very much for being a participant today.
My pleasure. Thank you.